Hey everyone! Today we are going to look at the next step, and that's the Bellman Optimality Equations. So in the last video in this series, we looked at where did the Bellman equation come from. We derived it, we started from basically the definition of the value function and worked our way to actually creating where does this equation come from. And so if you again remember, right, all the pieces of this equation are what we want is the value function, which is what is the future discounted reward I can expect to get given that I'm at some state S. That was the key idea. That's what we're trying to solve for. And the cool part about the Bellman equation is that we were able to set this up in a recursive way, because again, if we wanted to compute this directly without any kind of recursion or dynamic programming, that would mean we would need to, at every single state, take every single possible trajectory in our environment, every single one, and then average up the discounted rewards we get from it. That's obviously impossible because if you have a large environment, there could be nearly an infinite amount, right? An intractable amount of trajectories that we could take. And so for exactly that reason, we set up this new approach using dynamic programming and using this recursive form, which is the Bellman equation. And the Bellman equation, if you again don't remember, is essentially just our value of a state is the weighted average. So we do an average over our policy, where the policy is our weight. The policy prescribes what is the action we should take at a given state, right? So that's what the policy does. And these are weights. So if it's a deterministic policy, then it'll just be 1 for the action we take and 0 for all the other actions. Or if it was a probabilistic policy, then it could be, any number between 0 and 1. It just needs to sum to 1, right? Like a probability distribution. So we're going to go ahead and multiply our policy times all of this stuff here, which is going to be, if I take this action at this state, I can expect to get, or I will get, the environment will provide me this reward, right? This is the reward the environment provides me. Hey, you made it to this new state S prime. And then I'm going to add to it the discounted, by a discount factor, the future values, right, of the next state. And so this is what makes it recursive, right? My current values of the current state, the values of the current state, is a sum of what's the reward I got for the action I took, plus the discounted of the future state's values. And that's what makes it really cool and recursive. And we of course weight it by our probability of actually reaching a state, because if you again remember, not all environments are perfect, right? Some are stochastic. And so we looked earlier, if in your ice world or your frozen lake environment, you might mean to go forward, but you might end up going left or something because the floor is slippery and you slipped. So the environment can also be stochastic. So we will average over the stochasticity, right? All the possible next states I could get into and all the rewards I could have gotten. And so this was the key idea with the Bellman equation. But there's one big glaring issue that we haven't dealt with yet. And so we'll come back to that. The question is, what is this? What is the policy? Remember, the policy is what action, right? What action at state S? That's basically the question it's trying to answer. But that's the question we're trying to answer, right? This is what we want in the end. We want the policy. We want to know what action should I take at a given state. And to say that if this is the thing we need, and it's a part of the equation, then everything is messed up, right? We want this. This is the final thing we want from our training of a model on an environment. And if we don't have this, then we can't even, how can we solve for something if we don't even have the thing that we need? And so we have a problem, right? The computation of our values, this whole recursive Bellman equation, assumes that you have a policy. And so this is why I prefaced the last video on this, saying that this value equation is finding the values for the current policy pi, right? The current policy pi. But the question is, how do we actually find pi? What do we do? Because obviously this operation is not possible. We can't just take the sum over a policy when we don't really even have a policy, right? We don't know what the best policy is. And so we're going to be looking at some methods in a future video, in the next video, namely policy iteration, that will solve this. But let's just set the stage here with what are some of the Bellman optimality equations. And so first of all, let's just kind of recap ourselves. We have actually two types of value functions, right? We have state value functions. What is the value, right? The future rewards I can expect to get from a state. And we have action values, or also known as Q values. What is the value I can expect to get if I was at state S, but also took action A? And our value function, or state value function, is basically just the weighted average, or we're just averaging over, or just summing together across all the different actions we can take of our Q values. And so this is really what we're doing, right? Our values is just a weighted sum over our Q values, right? So just some discrepancy. Whenever I say values, I'm going to try to be specific if I'm talking about state values or action values, but state values are typically noted with V, action values are typically noted with Q. They're also known as Q values. So there we go. So this is kind of a little bit of a setup. So the optimal value function, right? What is some using star as my operator for like what's the best value function? Because that's what we want in the end, right? In the end, we want the optimal values, not just the optimal value for a specific policy, right? Like what are the optimal values for a specific policy, but just in general for this environment, what is the optimal values? And the only way to find that is let's go ahead and try all the different policies. We're going to try all the different policies possible in our environment, and then we'll compute our values. So again, we're going to pick a policy and then solve the Bellman equation. And then pick another policy, solve the Bellman equation. Pick another policy, solve the Bellman equation. And then just repeat this through all of the possible policies. And once you have all the policies, then go ahead and pick the one that gave you the highest value function for all the different states. And so this is known as the optimal value function. But as you can imagine, this seems crazy because the policy is A given S, right? It's what action should I take at a given state. But imagine how many you could do. In the grid world scenario, we have at every single state 4 actions we can take. We can go up, down, left, right, which means if we have 16 states, that means we have 4 actions to the power 16 possibilities, right? It's going to be 4 possibilities times 4 possibilities times 4 possibilities. That is a lot of different policies for us to iterate over, right? It doesn't seem possible. And this is a super tiny environment, just 16 environments. If we had 1,000 or 16 states, if we had 1,000 states, then this would be 4 to the power 1,000, which becomes even more intractable. So this is clearly not a feasible way of just try every single policy and then pick the one that did best. And this becomes even more complicated, of course, if our actions are not discrete. What if we have a continuous action or anything else? But for now, we're just sticking to the discrete case. So we have a problem. We can't actually solve this. And we want the best policy, right? The best policy that gives us the highest values. And given a policy, we can actually solve the Bellman equation. So how do we get around this? Well, this is exactly what the Bellman optimality equations are. So what we do is we say that for our value function, for example, so this is our Bellman equation as written here. Instead of taking, so we want to iteratively solve this, right? Because we cannot just solve it directly, as we can see, because it would be ridiculous. So instead of trying to directly solve it, we're going to iteratively solve it. And we're going to say that instead of just trying to, sum over all of the different policies, so in this specific policy, sum over all the actions and keep on going, what if we took the max action? So our ideal policy, our best policy, is just going to be, as we solve, as we iterate, take the value with the max action. So whatever gives you the max amount of value for a given action, take that one. So at a given state, we're going to pick the value that gives us the action that gives us the highest value. And that's the key idea. We're going to just do this iteratively. Again, the implementation will solidify this a little bit more when we actually build it. But for today, just as a general idea, at every single state, we're going to pick the action that gives us the highest value. And that is our optimal value function. So we're replacing this weighted sum situation with a max operation instead, right? Pick the value with the max. And you would imagine that this would continue to work because every time you pick the best action, your value function will only get better. So you'll just kind of iteratively keep improving it until you're done, right? Until you've converged, let's say. And so that's the first key idea. That's our optimal value function. Similarly, we have an optimal action function, right? So same thing. we're going to try to find, again, we can't take a max over our policies because that's not possible. So we need to basically do something very similar. Here's our Q value function from before, right? So same as before, but notice that we do have a recursion here. It's just a little bit hidden from us because the Q values depend on the future values. But we know that the values can be written, right? The values can be written as the sum of the policy times the Q value, right? Just like we had earlier. So if we go back, if we remember, right, the value is the sum of our policy times the Q value. So we have that. And so instead of applying it to the value of the current state like we have here, we want to apply it to the value of the next state, right? S prime. So that means if S prime, that means it's going to be just everything gets a new prime on it. So it's going to be, what is the next action I take? So what's the next action I take at S prime, the next state? And then you multiply by its corresponding Q values. And so we can replace this value function here with its equivalent expression, right? These two are exactly the same thing. It's just when we had done it earlier, we did it just for V prime S, but now we have an S prime as well, kind of added on. And so that gives us this, right? Just like we had, we're just going to take that expression and plug it in. So this whole thing here was V pi S prime, right? So that's what that whole thing was. And now in the exact same way as before, we are going to, because this operation here, we don't want to do it because summing over every single policy is not possible when we actually start iterating. So we want an expression that doesn't include the policy. And that's, again, a max operation. Pick the next action that gives us the most value, right? Pick the next action that gives us currently the most value in this specific iteration of our Q values. And so there we go. We now have our optimal action function as well. And so these are just a couple key ideas. So let's just recap. The problem with this equation here, our original Bellman equation, let's go back, the original Bellman equation, is that we cannot solve this. And we don't want the policy to be a part of our Bellman equation. Because if the policy is here, that means the only way for us to solve it is by iterating over every single possible policy. So if we can do a little bit of work and get rid of the policy, basically the dependency on having our policy in here, by defining our optimality equations like this, notice there's no policy in here at all. It's just for the values, it's a max over A. For the Q values, it's the max over A star. Then we can now solve this without really worrying about the policy directly. We're going to iteratively solve for it. And that's the key idea. Now, another intuition that you can get from this is in the value function, all we want is the state, which means what can we control? If we want the value of a state, then I can control what's the action I take at that state. Right? That's the key idea. If I'm at a state, I want to pick the action that maximizes the value of that state. On the other hand, when we have a Q value, which has a state and an action, right? So we're at a state, we took some action A, and it sent us to S prime, right? The next state. What is the only thing I can control at this point? Well, the next thing I do is the next action prime. And that's why we have the max over the action prime here, right? The next action that we take. So that's the entire purpose of the optimality equations. Let's just get the policy out of there, because as long as there's no dependency on the policy, then we don't have to break our heads over this. We don't need to max over this pi, because maxing over this pi or our policies or all possible policies is intractable, right? It's not a feasible thing to solve. And so by removing it, getting rid of it from our Bellman equation, essentially, we arrive at our Bellman optimality equations. Now you might be asking, like, why does this even work? Does this converge? Is it actually optimal? And the proof for this is a little bit out of the scope, I think, for a beginner, because I'm trying to make this as simple as possible for as many people as possible. It requires a little bit more mathematical rigor. There's a thing called the contraction mapping, and then there's the fixed point theorem, the Banach fixed point theorem. I'll just give the super quick overhead here, or just an idea here. The T that you see here is the Bellman operator. That's the Bellman Bellman operator is the way they write it. So that's the Bellman operator. And a contraction mapping is when the Bellman operator applied to some value function v, and then a Bellman operator, the same Bellman operator, applied to another value function, which we call w here. If the infinity norm, which we'll talk about in just a second, if the infinity norm, the difference between the Bellman operator applied to v minus the Bellman operator applied to another value function w, is less than or equal to some constant lambda times just the difference between the value functions, and again, the infinity norm, then we have something known as the contraction mapping. Now, in the literature, you won't see lambda here. You're going to see beta. And the rule is that beta must be between 0 and 1. If beta is between 0 and 1, and this property holds, then you have a contraction mapping. In our case, our lambda, our discount factor, is between 0 and 1, right? Our discount is between 0 and 1. So that's why our beta in the original contraction mapping literature is going to be lambda. So that first part kind of solves itself. The second part is, what is infinity norm? If you know a little bit about math, you'll know that the infinity norm is also called a max norm, right? A max norm. And we see the max right here, right? The max has arrived, and this is why the max is necessary. So we have a max and we have our constant. And again, I'm not going to go into too many details here, but as long as these two things are true, then you can show that the Bellman operation, this entire Bellman equation, everything we did, is a contraction mapping. And then the Banach fixed point theorem says that if you have a contraction mapping, then an iterative application, so that's our goal, right? We want to iteratively solve this. An iterative application of this contraction mapping T will converge to a fixed point. And fixed point means if we have, let's say we got to our optimal value function v star. That's the optimal value function for this environment. If we get to it, then applying our contraction mapping T to the optimal value will just again return the optimal value, because we've gone ahead and converged, right? There's nothing else to change. And so again, the proof of this optimality goes into a lot more mathematical rigor than I want to go into, because it's not as approachable. You need to have some better knowledge about metric spaces and things like that. But the key idea that I want everyone to take away is this. The optimality equation essentially finds a way to iteratively solve the Bellman equation without needing the policy. And we do this by using the max operation to replace it. So instead of saying that, oh, I want to just take the weighted average over the existing policy and yada, 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 let's go ahead and say that to update my value function, I'm going to take the action that gives me the highest future value. Or to update my q value function, I'm going to take the next action, right, the a prime, that maximizes my future q values. And that's the key idea. This is going to click when we actually implement it, so you'll kind of see a lot of these things in practice. But I'm going to call it here, right? This sets us up for the policy iteration. So I will see y'all in the next one.